Hello, am I audible?
Yes, sir.
Okay. And you can see my screen, right? Okay, so let's start. So I'm Bhargav. I'm one of the TAs for this course. I generally take problem solving sessions on Saturdays from 4 to 6, but last Saturday I had to cancel the session. So this is a makeup session for that cancelled session. And what we'll do is we'll first solve some problems based on week 5 assignment. And after that, we'll solve some problems based on week 6 contents. Okay. So let's start. Yeah, yeah, okay. So the first problem is choose the option or options that are incorrect for DES. The options are the round function in DES is a substitution permutation network. Option B is a block length of 64 bits and a key size of 56 bits are the shortcomings of DES. Uh, each S each S block defines an 8 to 1 function. Option D is a 1-bit change to a DES S-box input ensures at most 1-bit change to the output, and DES is secure against exhaustive search attack. So these questions are based on week 5 assignment. So you might have already solved that assignment and uh, answered these questions. So if you know the answer to this question, would you like to answer? You can answer in the chat. So what are the incorrect options among these five? Okay, so yeah, let me tell you the incorrect options are. Okay, let's go over this option by option. Okay, so the first option is the round function in DES is a substitution permutation network. Well, that is true. So DES is a crystal cipher network, but the in a crystal cipher network, in each and every round you have a round function, and in case of DES, that round function is instantiated or realized using a substitution permutation network. So DES sort of gives you best of both crystal network and a substitution permutation network. So option A is correct. Option B is a block length of 64 bits and a key size of 56 bits are the shortcomings of DES. Well, that is true because when DES was proposed, 2 to the 64 and 2 to the 56 were large numbers, but using the computational power that we have today, these numbers are not too large. And so, yeah, brute force attack can break DES, and that won't take too much time. So B is also correct. What about C? C says that each S box defines an 8 to 1 function. So this is incorrect because recall that in DES, each and every S box mapped a 6-bit input to a 4-bit output. So there are 2 to the 6 many inputs and 2 to the 4 many outputs. So an S box is a 2 to the 6 over 2 to the 4. That is 4 to 1 function. It's not an 8 to 1 function, it's a 4 to 1 function. So C is incorrect. The option D is a 1-bit change to DES to a DES S box input ensures at most 1-bit change in the output. This is incorrect because the S boxes of DES are designed in such a way that we get avalanche effect. That is, that is, the S box of DES are designed in such a way that when you change 1 bit of input of the DES S box, it changes at least 2 bits of the output. So option D is also incorrect. And option E is DES is secure against exhaustive search attack. Well, no cipher is secure against exhaustive. Okay, no computationally secure cipher is uh, secure against exhaustive search attack, and DES is also not secure against exhaustive search attack. So the options that you should pick for this question are C, D, and E. Is this fine? Okay, so if this is fine, let's move on to the next problem. The next problem is Select the options that are correct for AES. The options are A. It has 128-bit block length and uses a 128-bit key. Option B is it is a substitution permutation network. Option C is the SBox function in the subbytes operation is a bijective function. And option D is it is not proven to be secure against a computation adversary. So what are the correct options? Okay, so again, let's go over this option by option. Yeah, option A is it has 128-bit block length and uses a 128-bit key. Well, this is not true because DES is like three different block lengths, and like corresponding to each block length, you have different values of different key lengths as well. So A is not correct. Okay, what about B? It is a substitution permutation network. Well, it is a substitution permutation network. So B is correct. Uh, what about C? The SBox function in the subbytes operation is a bijective function. Well, if you look at the construction of the SBoxes in AES, yeah, they are invertible. So yeah, C is also correct. And it is not proven to be secure against a computational adversary. So we don't know whether A. So while we believe that AES might be is a secure cipher, it's just a practical construction of a block cipher. It's not a theoretical construction. So we don't know, or we don't have a proof of correctness of we don't have a proof of security of AES even against a computation adversary. So D is also correct. Is this fine? Okay, so if this is fine, we can move on to the next problem. So the next problem is as follows. Consider the following two encryption schemes. The first scheme is as follows. Here we are given that F is a secure PRP or pseudo-random permutation. Then the scheme is as follows. It chooses a key K uniformly at random from 0, 1 to the n. And then for a message M of length n over 2, it encrypts M by first appending or concatenating a random string R and n over 2-bit random string R to M, and then computing Fk of M concatenated with R. So this is how the encryption function is defined, and decryption function is defined analogously. So decryption of C is just M, where we first compute F K inverse of C, call that M concatenated with R, and the first n over 2 bits of that are message M. So that's what the decryption function or decryption algorithm outputs. And option and the second cipher is as follows. So now F is a secure PRF or a pseudo-random function, and the key is again chosen uniformly at random. The encryption function works as follows. We pick a random string R of length n, and for a message M again of length m, its ciphertext C is M XOR with Fk of R, but now the key is Fk of R. So we compute Fk of R, where R is again a random string. And decryption of C is analogously defined. So we uh, XOR C with this Fk of R, but the key is again Fk of R. So which of the following options is or are incorrect? So the options are 1 and 2 are both CCA secure ciphers. Option B is 1 is a CPA secure cipher and 2 is a CCA secure cipher. Option C is 1 is a CCA secure cipher and 2 is a CPA secure cipher. And option D is both are not CPA secure. And option E is none of the above. So which of these are incorrect options? Okay. So the correct answer is A is incorrect. Uh, yeah, A is incorrect. B is also incorrect. And B is also incorrect. And D is also incorrect. So three options are incorrect. And let's see one by one why all of these are incorrect. So the so what we'll first show is that both 1 and 2 are CPA secure. Okay. So let's see why 1 is CPA secure. So 1 is CPA secure because as F is a secure PRP, one is just a secure block cipher. So I think we saw in one of the, in maybe the third or the fourth week, that when F is a secure PRP and we encrypt and decrypt like this, then the resulting cipher is CPA secure. So we have seen before that the first cipher is CPA secure, and let's also see why the second cipher is CPA secure. Okay, so I think in one of the previous assignments, maybe week 3 or week 4, we saw that for R, which is picked uniformly at random from 0, comma 1 to the n, F this, or rather, let me write it down. If F is a secure PRF. And the intuition over here is this: since R is random and F Fk is a pseudo-random function, Fk of R is very close to random. So using Fk of R as a key uh, is fine. So we can use a pseudo-random key instead of a random key. And so yeah, this is also a secure PRF. And since this is also a secure PRF, uh, scheme 2 is just the following: R comma C, where C is M XORed with a secure PRF. And again, we saw in one of the previous weeks that this is a CPA secure cipher. We know that hmm, R comma M XORed with let's say G, where G is a secure PRF, is a CPA, gives the CPA secure cipher, I should say, because I haven't mentioned decryption. So both uh, 1 and 2 are CPA secure. So that already rules out, that already tells us that options B and wait, yeah, that already tells us that options B and option D are incorrect. And now let's look at option A. Option A says that 1 and 2 are both CCA secure. Now it turns out that 1 is CCA secure, but I couldn't figure out a like a simple formal proof for it. So what I'll just do is I'll just show that 2 is not CCA secure. So let's see that 2 is not CCA secure. I should pick a pen. Okay, so what we'll do is we'll just so recall the CCA secure game. What we'll do is we'll just show that there exists an adversary which wins that game with a non-negligible probability. In fact, the winning probability would be 1. So in this game, there is a so in this game, the adversary can ask encryption oracle queries as well as decryption oracle queries. And there is a pre-challenge training phase as well as the post-challenge training phase. Okay. But the adversary that we are going to construct would not need the pre-challenge training phase. And what it's going to do is it's just going to uh, directly move on to the challenge phase and uh, send two messages M0, M1 with, let's say, the same size. Yeah, I only let's pick. Yes, so it's going to send. Okay, let me write them the same size because we are just reading what tech please. Yeah. So it's going to send two such messages. Okay. What does the verifier do? The usual thing. It picks a key. It picks a key uniformly at random from 0, comma 1 to the n. That's n, right? Yeah, nothing is given. So let's just assume. Okay, yeah. Key is in 0, comma 1 to the n. So it picks a key in 0, comma 1 to the n, and it tosses a random coin. If B is 0, rather I don't need to know this. Then it picks R uniformly at random from 0, comma 1 to the n, and sends C is equal to, rather let me say, it computes C is equal to M MB XORed with FKR and sends R, comma C to the adversary. Now the adversary would make use of the post-challenge training phase, and in the post-challenge training phase, it's just going to make one query, and it's going to be a decryption query. So it's going to do this decrypt R C XORed with 1 to the n. And notice that this ciphertext is different from this ciphertext. So these two are different. So this is a valid query that the adversary can make in the post-challenge training phase. We call it in a post-challenge training phase. If the adversary is making a decryption query, that query cannot be the same as the response it received in the challenge phase from the verifier. So it sends this decrypt query and it gets a response. Let's call that response M. And then here's what the adversary does. It checks if M XORed with 1 to the n is the same as M0. If yes, then B prime is 0. If no, B prime is 1. and it sends B prime as its response, as its output to the verifier. Okay. So now let's analyze the success probability of the uh, uh, adversary. Okay. So what is this probability? Probability, rather let me do it like this. This would be simpler. Okay. So what is C? Okay. So first of all, observe that the adversary is clearly probabilistic polynomial time because all it does is just generate two messages of length n and perform this computation, which is also, yeah, just linear in n. So A is efficient. Now, let's analyze what's happening over here. So, what is C? C is MB XORed with, oh, wait, yeah, instead of F, I should write this over here because this is this, right? Yeah. So, MB is F K R. Because this is what our second cipher, second encryption scheme is, right? So this is C. So what is M going to be? M is going to be the decryption of C. So M is this. So M is a decryption of this XORed with 1 to the n. But let me write it. M is a decryption of K R comma XORed with F K R. I want this 1 to the n. And by definition of this encryption scheme, this is just, yeah, uh, MB. So the entire message XORed with, and as we can see, this is just, so XOR of this with this is just 0. So we get that this is MB XORed with 1 to the n. So M is MB XORed with 1 to the n, and therefore M XORed with 1 to the n equals to MB. Okay, so now that we have this, we can easily analyze the success probability. So what's the probability that B prime is equal to 0 given B equals to 0? This is the same as probability M XOR 1 to the n is equal to M0 given B is equal to 0. And this is exactly the check we are performing, right? Okay, so from what we just saw, so from this is just probability that because B is 0 and B is M0 equals to M0 given B equals to 0, which is just 1. Okay. And what is this? Probability B prime is equal to 1 given B equals to 0. Again, probability mx over 1 to the n equal to m0 given B equals to 1. But when B equals to 1, MB is M1. So we have, this is 0. So the difference between these two probabilities Yeah, I calculated the wrong probability. I should have calculated. Yeah, so in the distinguishability, yeah, we are supposed to let the other probability, right? We are supposed to differentiate between these two. Probability P prime is equal to 0 given B equals to. Yeah, so M XOR 1 to the N is MB, but MB in this case is M1 is equal to M0 given B equals to 1. This is 0. So the difference is 1, which is non-negligible. So A is a valid CCA adversary for second encryption scheme, and so the second encryption scheme is not CCA secure. So that also tells us that A is incorrect. So A, B, and D are incorrect. Therefore, option E cannot. E has to be correct. Sorry, so we cannot pick option E because option E being correct would say that none of the above are incorrect, but already three are incorrect. So option B cannot be picked. E cannot be picked, and it turns out that option we are only left with option C, and that is actually correct. So we it it is true that one is CCA secure, but I couldn't like come up with any simple proof for that. Is this fine? So if there are no questions, let's move on to the next problem. Yes, the next problem is the following. Select the correct option or options for MAC. It is message authentication codes. The options are the tag verification algorithm must be randomized. Option B is MAC for fixed length messages constructed using PRF is SCMA secure. A head of organization sending a broadcast email to employees is an example of an application that requires encryption but not authentication. And in streaming MAC, we do not need to know the message length beforehand. So which of these options are correct? Okay, so let's go over this option by option. The first is the tag verification algorithm must be randomized. Well, if the tag verification algorithm is randomized, then, oh yeah, okay, yes. In option B, the PRF is secure. Okay, so secure PRF is sort of a misnomer because how we define the PRF? So PRF is by definition a function which is difficult to distinguish from a totally random function, right? So yeah, PRF and secure PRF are the same thing. Okay, yeah. So if that is fine, let's go with this option by option. So yeah, the first option is the tag verification algorithm must be randomized. Well, the tag verification algorithm is randomized. Then given the same message tag pair, it can give you different outputs. Okay, so what I said was the following. Okay, so what is a PRF? A PRF is any function which is computationally indistinguishable from a totally random function, right? Okay, so what is a secure PRF? So secure PRF is the exact same thing, right? Because by the very definition of PRF, it is supposed to be indistinguishable from a uh, totally random function. So it doesn't matter whether we say that the PRF is secure or not. So it doesn't matter whether we use the term secure PRF or just PRF. Because a function which is not a secure PRF is not even a PRF. It's not even a pseudo random function. Because you can distinguish it efficiently from a totally random function. Is this fine? Okay, yeah. So yeah, we were at option A, right? Yeah. So okay, if the tag verification algorithm is randomized, then given the same message tag pair, it can give you different outputs. But the tag verification algorithm, what is it supposed to do? If you give it the correct message tag pair, it should output one, right? So if it were randomized, given the correct message tag pair, it can sometimes output zero, it can sometimes output one. So in fact, the tag verification algorithm must not be randomized, it must be deterministic. So option A is not correct. What about option B? MAC for fixed length messages constructed using a PRF or a secure PRF is SCMA secure. Well, this we saw in class, right? So this is correct. Then option C is head of organization sending a broadcast email to employees is an example of an application that requires encryption but not authentication. Okay, now this is incorrect because here we also need authentication. Why? Because let's say you are an employee and you get an email, okay, and the person sending that email claims to be the HOD, right, or the head of organization. How do you know that the person is actually the head of organization and not some malicious party, right? You would only be able to figure that out if the email is also authenticated along with maybe being encrypted or not, right? So in this application, we also need authentication because otherwise a malicious party can send some email pretending to be the head of organization. So option C is incorrect, and option D is in streaming MAC, we do not need to know the message length beforehand. Well, this is uh,
Yes, sir.
uh, okay. I couldn't hear you. Can
Am I
you repeat?
audible, sir?
Yes, now you are audible now.
Yeah, sir. One question, sir.
Yeah,
So, what is the difference between PRF and secure PRF?
they are exactly the same.
Both are same, sir.
Yeah. Okay. So here's the
Oh,
reason. What is a PRF?
oh. Pseudo random function
Okay. How is it
from
defined?
domain to yeah, from a domain to another domain. That for domain may be larger than the usual domain.
Okay. Yeah.
Like
So what I was asking is, when do you say that f from domain, function f from domain A to codomain D is pseudo random? So when do you call a function pseudo random?
uh, I can't understand, sir. What is the pseudo random actually?
Right. So that is what I was saying. We say that a function f is pseudo random or a pseudo random function if f cannot be distinguished from a totally random function with non-negligible probability by any computationally bounded adversary, right?
Oh yes, yes, yes.
Right. And what is a secure PRF? What is a secure pseudo-random function? What is its definition?
If you are not distinguishable between randomized and another one pseudo random function, then it is a secure pair.
Right. But this is exactly the definition that I just said before, right? For PRF.
Oh, okay,
Right.
okay.
So yeah. So sort of when we say something is, we don't necessarily need to say that something is a secure PRF. Because when we say something is a PRF, it is always secure. The reason we say that is just yeah, it's just common practice. Yeah. Okay. So is this fine?
Okay, sir. Thank you.
Yeah. Yeah.
You can know, sir.
Yeah, so before this discussion, we saw that D was also cut. Okay, yeah, we were looking at option D, right? In streaming back, we do not need to know the message length beforehand. Well, that is true. That's, yeah, we saw this in class, right? So is this fine?
So one more question, sir.
Yeah.
May I ask?
Yeah.
So can you give an example for pseudo random function?
Okay, good. So right now we do not know of any provably secure PRF. So we do not know of any construction that we can prove is a PRF. Okay,
So far we don't have an example, right? In the
right.
lecture and all, there is no examples I have seen.
Yes. All we can, all we have been able to do so far is something like the following. If you have a PRG, you can construct a PRF. If you have a one-way function, you can construct a PRG and so on. So we do know of some constructions for PRFs, but those constructions assume something else. For example, let's say one-way function exists or something like that. Okay. So we do not know of any construction for PRF without any assumptions as of now. However,
Yeah,
we do have some practical constructions of PRF. So we do have some constructions which in practice work. Like in practice, so far we haven't been able to find any distinguisher for that construction, but we cannot prove that they are PRFs. And we saw some of these constructions in class, right?
yeah,
AES, DES, so on. Yeah,
yes.
yeah.
But we are assuming there is some PRF exist. Based on that some PRF, we are constructing more and more problems, right? Sir? May I right?
Right. So if you're talking about provably secure PRFs, then yes. So we are assuming that something exists, which we can't
Ah,
prove exists or not, and using that we are showing that PRS exists. For example, we showed that if there is a if there exists a PRG, then there exists a PRF, right?
yes.
So now to prove that PRF exists, we just need to show that PRG exists. But right now we can't do that.
Ah,
Correct.
right. Okay, sir.
Yeah.
Thank you.
Yeah. Okay, so if there are no other questions, we can move to the next problem. Okay, so the next problem is as follows. Which of the following is or are not true for max? A CBC MAC can only be used to generate tag uh, for fixed length messages. Option B is blockwise CBC MAC initialized with the initialization vector 1 to the n instead of the initialization vector being the number of blocks will be secure. A secure MAC does not maintain privacy of the underlying message, and all of the above are true. So which of these are true? Okay, so let's go over this option by option. CBC MAC can only be used to generate tag for fixed length messages. Well, no. So CBC MAC was a construction that we saw in class, right? Where we started off with a MAC for fixed length messages and constructed a MAC for arbitrary length messages. So CBC MAC is a construction which allows us to generate tags for arbitrary length messages. So option A is not true. What about option B? Blockwise CBC MAC initialized with the initialization vector 1 to the n instead of IV being number of blocks will be secure. Not exactly. So this, as we saw in class, if we use IV to be anything other than, let's say if we use IV to be 1 to the n or 0 to the n or anything like that, then our resulting MAC would be would just be prefix piece secure. So that was the first step of that was the first step, the construction of CBC MAC, right? However, if we want blockwise secure construction, then we needed to use an encoding which was prefix free. And uh, as we saw in class, if we set IV to be the number of blocks, then the resulting encoding is prefix free. And so the blockwise CBC initialized with IV equals to number of blocks would be secure, but uh, blockwise CBC initialized with IV equals to 1 to the n would not be secure. So B is also not true. What about option C? Option C is a secure MAC does not maintain privacy of the underlying message. Well, that is true. Secure MAC merely like authenticates the message. It does not. Unless you encrypt the message, you do not maintain the privacy of the underlying message. So C is true. And all of the above cannot be true because A and B are not true. So only C is true here. Is this fine? So there are no questions. We can go to the sixth problem. Okay, so then let's move on to the sixth problem. So the problem is as follows. Let f be a pseudo-random function. Consider maps that generate tags T for message M, which is divided into blocks as M1 to ML as follows. The first MAC is defined as follows. The tag T is the concatenation of FKM1 to FKML, where M1 to ML are all n bit messages. So the block size is n bits. And in the second construction, tag is generated by concatenating FK of these. What? There should be a concatenation over here. So in the second construction, we generate the tag as follows. The first over here, M1 to ML at n over 2 bits. Excuse me. So in the second construction, the block size is n over 2. So M1 to ML are n over 2 bits. And we first concatenate M1 with this. And by this notation, what do I mean is the following. So let me write it. I is the n over 2 bit binary representation of the number n. So we concatenate M1 with the binary representation of 1, or M2 with the binary representation of 2, and so on. And then we compute Fk of all of these and concatenate these together. That is how we construct tag for in the second scheme. The question is, which of the above constructions are not CMA secure? So would you like to guess the answer? Okay, it turns out that neither of the two constructions are CMA secure. Let's see why. So recall the CMA security game. What we'll just do is we'll construct an efficient adversary for each of these two constructions. And here's our, so let's first show that A is not CMA secure. So you have a verifier and an adversary. So recall that in this game, the adversary can send some messages to the verifier, and the verifier is going to return the tags of those messages to the adversary, and then the adversary is supposed to forge a tag for a new message. So the message that the adversary sends are as follows. The first message is, let me call it M11, M12. The second message is M21, M22. And there is pretty much M11, M12, and M21, M22 can be pretty much anything as long as they satisfy this condition. So adversary sends these two messages to the verifier. The verifier sends the corresponding tags, which are going to be T1. Let me call them T1, T11 concatenated with T12, and T2, that is T21 concatenated with T2. So yeah, over here I'm just assuming L is 2. You can do this for any L, but yeah, And let's do the simplest case. Now, what will the adversary do? The adversary will, okay, first let me do this. So it's going to set M star as follows. M star is M11 and M22. And the tag T star is defined as T11 concatenated with T22. And it's going to send these M star T star to the verifier. Now, first of all, observe that A is clearly PPT adversary. It's clearly efficient. Furthermore, M star is not equals to M1 and M star is not equals to M2. Why? Because M11 and M21 are different and M21 and M22 are different. So M star is clearly different from M1 and M2 both. So M star is a new message. So if we show that T star is the valid tag for M star, then adversary succeeds with probability 1. And 1 is not negligible in N, uh, so this adversary can forge a tag with non-negligible probability, and therefore the first construction, that is the construction in option A, is not CMS secure. So now let's show that T star is the valid tag for M star. Okay, so the valid tag for M star is FKM1, sorry, FKM11 concatenated with FKM22. Okay. Now observe that what is T11? Okay. So T1 equals to T11 concatenated with T12. So this is M11. So T11 is going to be FKM11 concatenated with FKM12. And similarly, okay, so therefore T star is equal to T11 concatenated with T22 is just FKM11, FKM22, i.e. valid tag for. So the adversary is able to forge a tag for a new message with probability 1. And so, yeah, the construction in option A is not CMS secure. Now let's look at the construction in option B. Oh, page. Okay, so the most of the game is going to be the same. Actually, the entire game is going to be the same. So let me just copy this. Okay, so the game is just as before. The adversary sends M1 and M2 to the verifier. M1 is M11, M12, M2 is M21, M22. The only condition on M11 and M12 is only condition of these four is this, that these two are different and these two are different. The verifier is going to send the tags, and again, is now A wants to forge a tag on a new message. So the message is going to construct is M star M11 M22 and tag T star is T11 T22 and send M star T star to the verifier. Now, since M1, M2, and M star are the same as they were in option A, and we saw in option A that M star is not equals to M1 and M star is not equals to M2, M star is indeed a new message. So as long as we are able to show that T star is a valid tag for M star, it would be done because we would have shown that the adversary is able to forge a tag for a new message. Now let's show that T star is a valid tag for M star. So what's the valid tag for M star? So let's look at the scheme. What was this scheme? Oh yeah. So it's going to be Fk of 1 concatenated with M1 and Fk of 1 concatenated with M11 and Fk of 2 concatenated with M22. So it's this. So this is the valid tag for M star. So now let's look at what T star is. But before that, we need to look at what T1 is. T11 is T this and this is. So this is going to be Fk of 1 concatenated with M11 concatenated with Fk of 2 concatenated with M12 because M1 is M11 M12, right? Similarly, T2 is going to be, oh sorry, it's M21 we have concatenated with Fk of, therefore T star, which is T11 concatenated with T22 is what? Fk, the T11 is just this concatenated with Fk, T22 is this, right? But this is exactly the same as this, right? So A equals to valid tag first. Yeah, so again, the adversary was able to forge uh, a valid tag for a new message, M star. So again, this scheme B is also not CMS secure. So neither A nor B is CMS secure. Is this fine? Okay, so if this is fine, let's move on to the next problem. Okay, yeah, we are fine. Okay, so the problem is as follows. Consider the following map for two n-bit messages The key generation algorithm just outputs a random key of n bits, and the tag generation algorithm takes a message M1 concatenated with M2. Here both M1 and M2 are n-bit are strings of length M, and the tag it outputs is Fk of M1 concatenated with Fk of M2. So the question is this MAC secure? That is this MAC CMS secure? Because this is a deterministic MAC. So we like to guess whether this is CMS secure or not. Here's the hint. It's very similar to the previous question. Okay, so this MAC is not CMS secure. So the answer is no. It is not CMS secure. So let us construct an efficient adversary for this scheme. I think the adversary is going to be exactly the same as before, or mostly the same as before. Yeah. Again, it's just going to send two messages. Jana M11 concatenated with M12 and 2 is 2 concatenated with M22. M11, M12, M21, M22, just like in the previous question, can be almost anything as long as they satisfy this condition. Oh, what am I? M21 is already been written. M12 is not equals to M2. That is, each and every block of these two messages are different. What's the verifier going to do? It's going to send tags T1, let's we call them T11 concatenate T12, and T2 is T21 concatenate with T2. Now, what the adversary will do is it will generate this message, and that is going to be T11 concatenated with T22. Yes, so the adversary is exactly the same as the one in the previous question. I could just copy paste it instead of writing. Yeah, so this is the message tag file it's going to send to the verifier. Now, again, as in the previous question, m star is not equals to m1 and m star is not equals to m2 either. Why? Because it's different from m1 because uh, m1 is m11, m12, m star is m11 and m22, and m22 and m12 are different. So that's why it's different from m1, and it's different from m2 because m1, m1 and m2 are different. So it's different from both of them. So M star is indeed a new message. So if we show that T star is a valid tag for M star, then just as in the previous question, we would be done. We would have shown that this is not a secure map. Right. Let's show that T star is a valid tag. So what's the valid tag for M star? So from the definition of the scheme, it's going to be Fk M11 concatenated with Fk of Fk of M22. Yeah, so this is going to be the valid tag. Now, what is T1? It's going to be Fk of M11 concatenated with Fk of fk of m12. Why? Because in this case, the uh, two message blocks are M11 and M12. So you would put M11 over here or M12 over here, right? Similarly, T2 is T2 and contracted with T22 and it is, I lost connection. So I think I lost connection for a while. Am I audible now? Hello? Am I audible?
Yes, sir.
Okay, yeah, thanks. Okay, so yeah, I was here. Yeah. T2 is going to be T21 contracted with T22 and it's going to be this. So now what's T star? This is how we have defined T star. And T11 is the first part of the T1, so it's M11. And T22 is the second part, so T22 is this, which is, but observe that this and this are exactly the same. Oh, sorry. This and this are exactly the same. So equals to, so T star is indeed a valid tag for M star. And yeah, M star is a new message. And the adversary has been able to forge a tag for M star, so this scheme cannot be CMS. Is this fine? Okay, so if there are no questions about this, let's move on to the next. So the next problem is as follows. Which of the following options is or are correct? The options are in the CCA attack model, the adversary can ask for decryptions of any ciphertext of their choice. Option B is the CCA security model captures the passive adversary. Option C is the CCA model captures a malicious or active adversary. And option D is providing decryption oracle to the adversary does not provide any additional power to the adversary. So which of these are incorrect? Okay, so let's go over this option by option. So the first option is in the CC attack model, the adversary can ask for decryptions of any ciphertext of their choice. Well, this is almost correct. So recall that in the CCA security game, there is going to be a pre-challenge training phase, a challenge phase, post-challenge training phase, and uh, the response phase. Okay. Now, in the pre-challenge training phase, the adversary can ask for encryptions of any messages and decryptions of any messages. Then in the challenge phase, it's going to send two messages, M1 and M2, and the uh, verifier is going to randomly encrypt one of these and send the corresponding hypertext C. Okay. Now, in the post-challenge training phase, there is one restriction on the decryption oracle queries that the attacker can make, and that restriction is the following. If C is the ciphertext that was sent by the verifier in the challenge phase, then the adversary cannot uh, query the decryption oracle for C. And the reason for this is if it can query decryption oracle for C, it could find out which message was encrypted M0 and M1, and the game would be meaningless, right? So option A is almost correct. There is just one restriction on which decryption, which ciphertext. So there is just one ciphertext for which it cannot ask for its decryption, and that is the ciphertext change sent in the challenge phase. So because of this one exception, A is incorrect. Option B is CCA model captures the passive adversary. Well, that's also incorrect. The CPA model and the eavesdropper only or ciphertext only attack model. Those two models capture passive adversaries, and CCA captures an active adversary or a malicious adversary. So B is also incorrect. Option C is the CCA model
Okay.
captures the malicious adversary. Well, that is true.
Hello, sir.
Yeah.
Why the option A is incorrect, sir?
Okay.
Please.
So yeah, as I said, there is just one restriction on which queries or which decryption. So there is just one restriction on the decryption oracle queries that the adversary can make. Okay. So if so, what is the adversary going to do in the challenge phase? The challenge phase, it will send two messages M1 and M2 to the verifier. The verifier is going to decrypt one of these randomly and send the corresponding ciphertext C back to the verifier, back to the adversary, right? Now, recall the CCA security game. In the CCA security game, there was one restriction on which decryption oracle queries can the adversary make in the post challenge training phase. And that restriction was that it cannot query the decryption oracle for the ciphertext C. Do you remember this?
Yes, sir. Yes, sir.
Right.
Ah.
Yeah. And why is this? Because when if it can query for the ciphertext C, then it would find out whether M0 was encrypted or M1 was encrypted. With probability 1, it's going to be able to say which one was encrypted, and the game would be meaningless, right? So to make the game meaningful, we did impose this one restriction on which decryption oracle query the adversary cannot make, and that restriction was that it cannot query for the ciphertext it obtained the challenge phase. So just because of this restriction, the statement that the adversary can ask for decryptions of any ciphertext of its choice is incorrect. There is just one ciphertext for which it cannot ask for decryption. Right? Is this fine?
Yes, sir. Got it.
Yeah. Okay. So there are. Oh yeah. So we were at option D, right? So the option D is providing decryption oracle to the adversary does not provide any additional power to the adversary. Well, this is false because as we saw in one of the previous questions, I think this question. So as we saw in question 2, uh, this, okay, so let's look at the second scheme in the question 2, right? It showed that it is CPA secure, but not CCA secure. So there are schemes which are CPA secure, but not CCA secure, right? And if I were to give decryption oracle to the adversary would be able to break all such schemes which are CPA secure but not CCA secure. So providing decryption oracle to the adversary does give additional power to the adversary. So option D is also false. As option A, B, and C, D are false. Uh, is this fine? Okay, so in that case, let's move on to the next problem. So the problems that we have solved so far were based on week 5's assignment and its week 5's content. So now let's solve some questions based on week 6 content. Okay. So the first problem is the following. Choose the incorrect options. Option A is R, comma product is a group. Here by R, I mean the set of real numbers. Okay. Option B is R set minus 0, comma plus is a group. That is the set of non-zero real numbers with addition as a group. Option C is Z minus 0, comma plus is an abelian group. Option D is R minus 0, comma product is a group. And option E is Q. By Q, I mean the set of rational numbers. The operations plus and product is a field. Oh, by the way, I forgot. Well, here's by Z, I mean the set of integers. So, which of these options are incorrect?
So A,
A is
B,
definitely okay. A is definitely
E,
incorrect.
incorrect.
So,
Since
A is
zero
incorrect.
element is here, so inverse is
Yes,
not up here.
right.
Uh,
Then you said B is also incorrect, right?
uh, for B is also.
Yeah,
Since zero identity is not there.
right. What about C?
C, there is no identity. Zero
Right, same reason. It's also
uh,
incorrect. What about D and E?
is group.
Yeah, D and E are correct. Both of those are
Yeah,
groups. Okay, yeah,
D and E are correct.
yes, yeah. Okay, so let's just go over all of these ones to ensure that everyone is understood. So R comma multiplication is not a group because in a group, for every element, you need an inverse. That is, for every x in R, 1 over x should be in R. But when x is 0, 1 over 0 is not a number, so it's not in R. So 0 does not have any inverse, and so R comma multiplication is not a group. What about option B? Well, for a set, for a system to be a group, it must have an identity. That is, there must exist an element E such that for all x in R, x plus E is equal to E plus x is equal to x, right? Now, such a number for real numbers is 0, but we are removing 0 from the set, so R minus 0 cannot be a group. For the same reason, Z minus 0 cannot be a group because the identity of addition is 0, which we have removed. Uh, R minus 0 comma product is a group because, okay, so let me quickly show you why this is a group. Yeah, so D is a group. Okay, so first of all, for all A comma B in R minus 0, AB is obviously a real number. Then for all A comma B comma C in R minus 0, we know that multiplication is associative, right? So we know that AB times C is equal to A times BC. So the associative property is true. Then for all A in R, we know that A times 1 equals to 1 times A equals to A. So 1 which, oh sorry, I should have written minus 0. So 1 which is in R minus 0 is the identity. And the last is for every element, an inverse should exist, right? So for all A, okay, I lost connection again. Hello, am I audible now?
Yes,
Yes.
sir.
Yeah, I lost
Yes,
connection
you
for a
are
moment,
audible.
but my screen is not visible, right? Let me reshare my screen. Can you see my screen?
No, sir.
Okay, let let me try to reshare. Is it visible now? Can you see my screen now?
Yeah, yes, sir. Yes, sir.
Okay,
It's
great.
visible.
So, yeah, before I lost connection, we saw that uh, this system in option D satisfies the closure, associativity, and the identity axioms. Now, let's see if uh, this set also has inverses. So, for all in 0, comma r, a times 1 over a is equal to 1 over a times a equals to 1, right? So, every element in this set also has an inverse. So, yeah, uh, this satisfies all four properties of a group. In fact, it's an abelian group because multiplication is also commutative. So D is correct. And similarly, you can show that E is also correct. Yeah, you basically have to do this, what we did over here, but for both the plus and product operations, and also show that plus and product operations are commutative, which we already know they are. Okay, so is this fine? Okay, so in that case, let's move on to the next problem. Okay, so the next problem is as follows. Yeah, it's quite a long problem. So let pi1 uh, defined as gen, tag generation, and tag verification to the subscript 1, and pi2 be 2 max. What does a key generation algorithm do? It just outputs a random key, a string from 0, 1 to the n. Now, it is known that exactly one of the max, pi1 and pi2, is secure. So, which of the following two constructions are also secure? The first construction is as follows. So it's pi equals to gen prime, tag gen and tag var, where, oh, this should be gen prime. Here, what does the key generation algorithm do? The key generation algorithm just outputs a random string of length 2n. Then, for a message m equals to m1 concatenated with m2, so where m1 and m2 are both n bit strings, the tag is generated as follows. We compute the tag using the first scheme over here for m1 and concat and key k1, and you compute the tag according to the second scheme using key k2 for message m2 and concatenate these two, right? And what does the tag verification algorithm do? It given m comma t, it says it outputs 1 if and only if T is T1 T, and T2, then T1 is a valid tag for M1 according to the first scheme, or T2 is a valid tag for M2 according to the second scheme. So this is the first scheme that we are proposing. The second scheme is very similar to the first scheme. Again, uh, key generation algorithm is just going to output a random string of length 2 to the n. And for a message M1 concatenated with M2, the tag generation algorithm also does the exact same thing. So what's the difference between the two? Well, the difference is in how they verify the tag. So now, given M comma T, the tag verification algorithm is going to output 1 if and only if T is equal to T1 concatenate T2 and T1 is the valid tag for M1 and T2 is a valid tag for M2. So the only difference between these two schemes is this. In the first scheme, if T1 is a valid tag for M1 or T2 is a valid tag for M2, we are going to accept. In the second scheme, we require that both T1 and T2 be valid tags. The question is, which of these two are secure max? So would you like to guess what the answer is?
Second one will be secure. B option.
Option B. Are you saying option B? I didn't hear you clearly.
Yeah, option B will be a
Okay,
secure
yeah.
MAC.
Okay, why? And what about why would option B be secure and not option A?
Because you have
Because it's taking two tag verification, right?
Right. Okay, so what can go wrong if we just verify like one tag?
I'm sorry, sir.
So what can go wrong in scheme A? So what can go wrong if we just verify one tag?
If any one of the tag is correct, then it is accepted in the first case, option A.
Right.
But in the second option B, both must be true. Then only it will be accepted as a secure MAC.
Right. So okay, but the question is, which of these is secure MAC, right? So what we need to look at is the following. Can I forge tags for a new message, right? So can I come up with a message, let's say M1 star, M2 star, and a tag T1 star, T2 star for both these schemes? So like, can you tell me how would you do this for the scheme in option A?
No idea, sir. Please, we will follow you.
Okay, so the question asks us to tell which of these is the secure MAC, right? Now suppose that given a message, suppose that we could not come up with M1 star, M2 star and T1 star, T2 star such that M1 such that T1 star is a valid tag for M1 star or T2 star is a valid tag for M2 star. Okay. Suppose we could not do this. Then option A would have been a secure MAC, right? Okay, so let me write that. Right. Suppose. Okay. Yeah. A is a secure MAC. Then only a computation adversary, rather any PPT algorithm. Wait, why am I writing 1, 1? Okay, so can you see my screen? 'Cause I think I lost connection for a while again.
No, sir.
No.
Okay, so let me
The
rejoin.
screen is not visible.
Yeah, let me join and reconnect. So let me change my network. That would be easier. Keep on getting disconnected every once in a while. Is it visible now?
Yes, sir. Screen visible.
Yeah. Okay. So in this question, we want to find out which of these are secure max, right? So suppose that we have the following. Any PPT adversary A cannot output a message M star and a text T star such that T1 star is a valid tag for M1 star or T2 is a valid tag for M2 star, right? Suppose this condition were true, then A would have been a secure MAC, right? Because this is just how a secure MAC is defined, right? So to show that A is not a secure MAC, we should somehow construct a PPT adversary A which can do this, so which can force the tag, right? And here's how we can construct such an adversary. So, what the adversary A does is the following. Mm, A asks for a tag T is equal to T1 for the message. Let's say 0 to the n, concatenated with 1 to the n. Then it sets 0 to the n concatenated with 0 to the n, and T star is mm, T1 concatenated with anything, doesn't matter. Let's just say 0 to the n. Now, while tag verification, so while 0 to the n need not be the correct tag for 0 to the n, that is, while the second check fails, the first check succeeds. I should put K2. Here it should be 2. Tag verification K1, 0 to the n, T1 equals to 1, right? So according to the second scheme, T star is a valid tag for N star. And so in the second scheme, we were able to forge a tag for a new message, right? The message 0 to the n concatenated with 0 to the n is clearly different from the message 0 to the n concatenated with 1 to the n, right? So the second scheme is not CMS secure. On the other hand, so the first scheme is not secure. On the other hand, the second scheme is secure because suppose that, yeah, let's say why B is secure. So suppose for the sake of contradiction, it is not. And there exists a PPT algorithm A which can forge a tag, right? Say it forces the tag for the message M star is equal to, let's say, M star 1, M star 2 as before. And suppose the tag is then, since we are performing both these checks, we have the tag verification 1, K1 star T1 star is equal to 1. And that is T2 star is the correct tag for M2 star and T1 star is the correct tag for M1 star, right? However, uh, which schemes were they? Pi1, Pi2. So now Pi1 and Pi2 are secure max, right? So we should not be able to forge tags for a new message for either Pi1 or Pi2. Now, since M star is a new message, either M1 star or M2 star has to be a new message. If M1 star is a new message, we have forged a tag for Pi1. If M2 star is a new message, we have forged a tag for Pi2, right? So in either case, we were able to forge a tag for one of the messages, and but that would contradict the fact that both of them are like at least one of them is secure, right? So is this fine?
Sir, shall we see the question?
Okay, yeah, yes.
here there are two max only given, right? Y1
Yeah.
by 2.
Yeah, so we have pi 1 and pi 2, and from those two, we construct two new maths in option A and option B. And we are asking, like, which of these are secure?
Okay, okay, okay.
Yeah. So, yeah, B is secure, but A is not. Okay, so if this is fine, let's move on to the next problem. Okay, so the next problem is about hash functions or collision resistant hash functions. So the question is as follows. If H is a CRHF, that is a collision resistant hash function, then the question is H prime defined as the concatenation of H of X with itself also a collision resistant hash function? So would you like to guess whether is is it a CRHF or not? Okay, so the answer is yes. The reason is the following. Suppose efficient PPT adversary or adversary can find x not equals to x prime. So it can find x and x primes are not the same, such that h prime of x is equal to h of x. Then h prime of, let me write this. So suppose that there is a PPT adversary that succeeds in finding a collision for h prime, right? What does this imply? Well, h prime x1 is just this. Which implies uh, h, a contradiction. Yeah, so the thing is, if x1, so if an adversary can find a pair x1, x2, which is a collision for h prime, the same pair is also going to be a collision for h. And since h is a collision resistant hash function, our assumption is that you cannot do this, right? So that implies that you cannot find a pair x1, x2, which is a collision for h prime either, right? So h prime also has to be a collision resistant hash function. Is this fine? Okay, so if this is fine, let's move on to the next problem. It is similar. So the next problem is the following. If h is a collision resistant hash function, then is h prime defined as h of x also a collision resistant hash function? Like, this is similar to the previous question. So would you like to guess whether it is or is it not a CRHF?
Yes, sir. It may be a CRHF.
Yeah, you are right. And like, what's the argument?
Since H is C, if it is not a H prime is not a CRHF, then it will
Yeah.
contradict to the H is to be CRHF.
Right. Yeah. The argument is exactly that. And it's similar to the previous question. So let me just write it. Suppose there exists PPT A which can find x1 not equals to x2 such that h prime x1 is equal to h prime x2, right? Then uh, h of x1 is equal to h of x2. So there are two cases. H of x1 is not equals to h of x2, right? In this case, I lost connection again. Yes, I lost connection again. Am I visible? Am I audible now?
Yes, it will be audible.
Yeah,
Yeah, visible.
yeah. So yeah, so if so there are two cases. If hx1 is not the same as hx2, in that case, x1 comma x2 is a collision, right? Why? Because x1 comma x2 are different, but their the value of their hash function is the same. So there's a collision, which is a contradiction, right? Why? Because h is collision with instant hash function. We shouldn't be able to find a collision pair, right? Case 2 is hx1 is equal to hx2. But in this case, yeah. Oh wait, yeah, yes, sorry. The first case was h1 yeah. So the first case was hx1 equals to hx2. In this case, I am claiming that x1 comma x2 is a collision. Why? Because x1 and x2 are different. However, the value of the hash function at both the places is same, and this is exactly what we mean by collision, right? So x1 comma x2 is a collision, but we shouldn't be able to find such a collision because h is a collision resistant hash function, and so this is a contradiction. The second case is hx1 is not equals to hx2, and in this case, y1 defined as hx1 and y2 defined as hx2 is a collision because y1 is not equal to y2, but h of y1 which is the same as h of x1, which is the same as h of x2 is equal to h of y2, right? Yeah, so in either case, if we are able to find a collision for h prime, using that we can find a collision for h. So h, since h is a collision resistant hash function, h prime also has to be a collision resistant hash function. Is this fine? Okay, yes, so this is fine. Let's move to the next problem. So this is again a problem about max. So consider the Mac defined as tag generation M1 to MV is equal to M1 times A to the V plus M2 times A to the V minus 1 plus all the way up to MV times A plus B, where all the where A and B are picked uniformly at random from the field ZP. Here P is a prime. And the length V is less than or equals to L for some fixed quantity L. Okay. So the question is this MAC information theoretically secure? Now, in class, we saw what an information theoretically secure MAC is. And we saw that a MAC which is very similar to this MAC is in fact information theoretically secure. So in class, we saw that this plus A to the V plus 1 gives us an information theoretically secure MAC. The question is, if I were to remove that plus A V plus 1, do I still get an information theoretically secure MAC? So would you like to guess whether this is an information theoretically secure MAC or not? Okay, so the answer is this is
I think
not.
no, sir.
Yeah, can you say that again?
Actually in a lecture, the polynomial is defined on V plus 1. Am I
Wait,
right, sir?
what is V plus 1?
The tag generation algorithm,
Right.
in that it defined on A power V plus 1.
No, so what I was saying is in the class, we saw this. But right now that APA V plus 1 is not present. So the tag generation algorithm computes tag for M1 to MV. Here are M1 to MV. And A and B together form a key.
A and B?
A and B are a key. So if I want,
Yes. A
right,
and
so
B are the key, yes.
right. So I should have written it like this.
Okay, sir.
Tag gen for key A comma B. Okay.
Okay.
Yeah. So is the question clear now?
Yeah, now clear.
Yeah. So would you like to guess whether this is information theoretically secure MAC or not?
So for no idea, sir, please follow. I will follow you.
Yeah. Okay. So I think this was also mentioned in the class, but it wasn't proved in the class. So sir mentioned in the class that this is not information theoretically secure, and here's the reason why. In fact, forget about information theoretically secure. It's not even CMS secure. Here's why. So let M okay, yeah. So let me just okay, what I'll show is like no, it is not. Not even CMS. So CMS security refers to computational security. Information theoretical security refers to like security against unbounded adversaries. So if something is not CMS secure, it cannot be information theoretically secure, right? Because if something is not secure against computationally bounded adversaries, then it is obviously not secure against computationally unbounded adversaries, right? So what we'll do is just we'll construct a computationally bounded adversary which can output a forgery. So here is the adversary. It just sends one message, which is 0 to the. Let me just assume that the size of M1 to MV, it is a block size is n. Okay, so it sends this. And yeah, let me just also say M1, M2, and yeah, so M1 comma M2 are non-zero. I don't think we need this, but yeah, let's just say it. What is V going to do? V is going to send a tag, right? And what A will do is it will set M star as M1 comma M2, T star as T, and send. It will send this message comma tag pair. Okay. Now clearly is not equals to M, right? Because M had three blocks, 0 to the n, M1 and M2. M star is just two blocks, M1 and M2. Okay. So as long as we show that T star is a valid tag for M star, we would have shown that we would have shown that this MAC is not CMS secure and therefore not information theoretically secure, right? So now let's just show that T star is a valid tag for M star. Okay, so what's the valid tag for M star? So, so valid tag for M star is according to this definition. So over here, V is just 2, right? So it is going to be M1 A to the V, which is 2, plus M2 A to the V minus 1, which is just 1, plus B, right? So this is the valid tag. Now let's see what T star is. So T star is a valid tag for like M, right? And what is M? It's 0, M1, and M2. Rather, yeah, just to be consistent with this notation, let me say it's M2. Oh yeah, yeah, it's fine, I think. Yeah. Okay, so over here our first message is 0 to the n. So over here 0 to the n, 0 to the n and M1 are the same. M1 and M2 are the same, and M2 and M3 are the same. Okay. So I just messed up the notation. I should have called this M2, M3, 2, 3, 2, 3 everywhere. So yeah, but so what's T? T is a valid tag for M. So T is going to be M1, which is in our case 0 times A to the V. V over here is 3. So it's 0 A to the 3 plus M1 A square plus M2 A plus B, right? But this is just M1 A square plus M2 A plus B. So T star is indeed a valid tag for M star. And so this MAC is not even CMS secure, so it's not information theoretically secure. So is this fine? So basically what is happening is because we can make the first block 0 unless we have this AV plus 1, we are going to run into that prefix free secure issue. Because over here, like this is the suffix of it, right? So that plus a to the, so this quantity was going to save us from, would save us from this issue, because yeah, in that case t would have been plus a to the 4, and over here we should have plus a cube. Yeah, so that plus a to the b plus 1 was very crucial in that construction that we saw in class. Is this fine? Okay, so if this is fine and there are no other questions, maybe we can end for today and meet this Saturday from 4 to 6, our usual time. So I'll just wait for a minute or two in case you have questions, and then we can end the session.
Excuse me, sir.
Yeah.
Sir, could you quickly explain the first part of the 6th and the 10th question?
Okay, what is the 6th question? Wait, first 10th question. Okay, so in the 10th question, in the first part, what did we do? So, uh, like we have two schemes, pi 1 and pi 2. And we want to show that this scheme is not secure. So this scheme is not a secure map. And the way we did it was the following. What we did was we queried the MAC, the new MAC for this, for any message. Okay. So we queried the MAC, the new scheme for this message. Now, what would that give us? That would give us a tag t equals to t1, t2, where t1 is a valid tag for 0, t1 is a valid tag for 0 to the n, and t2 is a valid tag for 1 to the n, right? Now, we computed forgery for m star equals to 0 to the n concatenated with 0 to the n. Now, these two messages are clearly different. And our tag was just t1 concatenated with 0 to the n, right? Now, t1 was a valid tag for m1, right? So sorry, t1 was a, this t1 was a valid tag for m1 star, right? Or which in this case is 0 to the n. So t1 is a valid tag for 0 to the n. So this first check, so over here m1 would be 0 to the n, t1 would be t1, and this check passes, right? Sure, this check fails because 0 to the n might not be the correct tag for 0 to the n, right? So this check might fail, we don't care. But because we are only computing OR over here, right? Is this fine?
Yes, sir.
Yeah, and now let's go to problem 6. Okay, yeah. So over here we have, so let F be a PRF. Consider max that generate tags T for message this. Okay. So again, we are going to, so we want to show that this is not secure. So we are going to compute a forgery, right? So what we are going to do is the adversary is going to query the MAC for messages M1 and M2, which are defined as follows. The only constraint on M1, M, like these four values are that these two must be different and these two must be different. Okay. So what is it going to get? It's going to get two tags. And then what the adversary would do is M11, M22. So it takes the first part from here, the second part from here, and it sets T star to be T11 concatenated with T22. It outputs M star T star. Now M star is clearly not M1, it's clearly not M2 because these two are different. So it's not M2 and these two are different. So it's not M1. So M star is a new message. So as long as I can show that T star is a valid tag for M star, I'm done. Right. So let's first look at what the valid tag for M star is. according to the scheme, it's going to be Fk of M1 star concatenated with Fk of M2 star, right? What is M1 star? It's M11. What is M2 star? It's M22. So this is the valid tag for M star. Now what is T1? T1 is T11 concatenated with T12. But from the scheme, similarly, from the scheme, T2 is going to be FKM22, right? So T star, which is the concatenation of these two, it's what is it going to be? It's going to be FKM11 concatenated with FKM22, right? But this is exactly the valid tag for M star, right? So T star is the valid tag for M star. And so we were able to forge a tag for a new message. Is this fine?
Yes, sir. Sir, in this message M1, you have written M1, M11 and M12. Are
Right.
these blocks of this message M1?
Yes. So these are blocks of length n for the first scheme.
Oh,
Yeah.
okay. It means each of message M11 and M22 are of length n. Okay, okay.
Yeah.
Thank you, sir.
Yeah. Okay, so if there are no other questions, we can end the session. Thank you.